Hello all, welcome back to the last session in our reinforced concrete course. We are in the topic called Prestressed concrete. I hope you would have understood. So to understand this prestressed concrete, actually you don't need to fully understand our reinforced concrete structures, but you should know at least what is reinforced concrete structures, because we are reinforcing the concrete. That much you should know. Okay. And if you have good experience, if you had a good experience by solving all the problems what we have solved earlier, so that you will know how much MPa yes steel can take. What is the actual MPa you would have solved so far for mild steel? We would have used at clue 250 MPa. For HOST bars, you used bars of 415 MPa. So 500 MPa, another bar is. So what you would have understood, we are reaching a yield value. We are going to apply a load in the beam, and the beam will start to yield. Correct? When you are applying, a beam will deflect and the steel will start yielding, and it will reach. You can apply up to a 400 MPa. Forget the factor of safety. I'm just telling you logic. So after reaching 400 MPa or 415 MPa, 500 MPa, the steel will start yielding. Correct? So that's the story of reinforced concrete. I hope you would have known that story at least. What is bending? What is simple bending? What is concrete structures? What steel is doing there? I hope everything we have discussed. Okay, in the previous classes. Now we cannot explain. It is a separate subject. Prestressed concrete is a purely separate subject. We cannot. I'm assuring, I promise you, I can never make you to fully understand. This is a full semester course. I should teach you at least like 10-15 hours, like a prestress, like a RCC itself. It is a separate. But I can make you cover what is required for your exams, whether it is RRB, state selection, or SSC, ISRO, any type of exams. What point you should know. So far, if you have seen my teaching, we are teaching only to the core. What you want to know, what is single reinforced, what you are expecting from that. Okay, we are not I hope you understood, if there is a figure, okay, there is a story, you don't know. If the consider you are seeing a movie, you will never know that what the shirt color of your hero, pant color of your, whether what brand of shoe he is wearing. I don't want to explain all you that. Correct? So I will tell you only the story, what hero does, how he flattens the heroine, and then what is the final climax, how he kills the villain. Only that story I'm teaching you. Okay, I'm not explaining you the surrounding environment. I don't care. Okay, please, you don't care also. I am going to explain only to the core. But if you are more interested, you can visit other books, standard textbooks, to learn more. Okay, so I will try to finish in this lecture, make you to the core. What is pre-test? What are the problems you can expect from pre-test? If somebody asks you in interview, at least you can answer them. Okay, so actually, what is pre-stressed concrete? You see the right side figure, first left side figure. You see reinforced concrete. When we are applying a load, there is a beam. What is reinforced concrete structures? There is a beam. Mostly we will take a beam. Okay, in pre-stressed this syllabus also we are going to see beam. We are not going to see pre-stressed column like your electrical towers or something, or not like a dam girder and all. Girder is a beam actually. We are not going to see other structures like what we have seen, column, slab, etc. Pre-stressed slabs and all. There are pre-stressed slabs actually, but we are going to see only the theory of pre-stressed beam in this topic. Okay, but general theory will apply to everyone. What are the losses, pre-stressed, everything will be applied to all the topics. We are going to see only pre-stressed beam. Okay, so first you should know what is reinforced concrete. I hope you know. So when you are applying a load, the beam will bend and the crack will develop at the tension zone. Correct? When the load exceeds the capacity of your beam, the crack will develop. Okay, so in this the same figure, you can see right side, the lorry figure, the truck figure. First two figures are same. If it is a reinforced concrete beam is there, when the truck is moving on, there will be a crack develop at the tension zone when the load is very heavy. Okay, now in pre-test, what we are going to do, we are going to provide a steel. Okay, steel, in this time there is no reinforcement bar. It is not like a reinforcement bar. In pre-test, don't consider it as a bar. We are going to, it will be a tendon. It is like a string of wires, like 10 wire, 15 wire, 100 wires, 200 wires combined to form a tendon. You would have seen like a mooring rope which is used to tie the ship, or I hope, try to imagine it is a tendon. You just google it. Okay, so that's what we are going to do. What we are going to do is we are going to stress the beam before applying the load, so that the beam will bend in upward direction. Okay, so when the load is acting, nothing will happen. The beam will come to the normal. You can see the figure. With the dead load, means there is no structure, there is no load applied. The beam will look like this. When the load is applied, when the service load is applied, the beam will become straight. Okay, so when you are applying further extra load, then only the beam will start bending, then the tension will develop, then the crack will come. So this is a understood, right? This is a very new case. It's not like how what are the theory you have studied, totally it will change in pre-stress. Okay, so you will understand more. You can pass and understand the figure, or we will learn more in next coming slides. So this is another explanation. You see the first figure in the right side is like a same RCC beam. When you are applying a load, the beam will bend and there will be a tension crack developed at the bottom. So same for the cantilever beam. I have shown for both. For sagging and hugging, no, same story. When there is a tension, the crack will develop when your load is exceeding. But in pre-stress, the second figure, we are going to stress the beam from the side so that the beam will deflect in upward direction, and when you are applying the load, the beam will become straight. Okay, how much you can stress, how much, see, you see there is a deflection, right, in the second figure. From the right side second figure, you can see the beam is slightly bent. How much, up to how much you can make the beam bend is the deflection should not be greater than span by 300, or it should be less than 300. Okay, so this is the definition. As I already told you, pre-stress concrete is a same concrete, but here we are applying initial compression. We will be compressing it from the side, so that before applying external load, so that the stress from external load are contracted in the same way, then during the service load it will become a straight beam. Okay, if it is straight, then you apply a further load extra. If you want, if you sudden reason, if there is an earthquake or wind load extra, the extra load is coming, then it will bend. Okay, so the capacity is double, triple, 4 times of the RCC beam. Okay, so this is the one of the biggest advantage, but it is very costly. I hope you understood. Steel you will get in common stores. You have to, pre-stressing is a very high technical people required to stress it up to 1000 MPa, 1500 MPa. It's very dangerous to do in for every residential building. So it is common for bridges, deck, girders, everywhere. Okay, pre-stressed slabs and all we will use for port and harbors, offshore structures, offshore concrete structures, obviously. So there and all we will use this pre-stressed. Okay, not for a simple residential building, which is very easy with RCC. Okay, and main reason is for house you are not going to expect some big load, right? You would have learned 70 kilonewton meter, 80 kilonewton meter, 100. That itself a very big number for a residential building. So this where the load is coming around 1000 MPa, there we will use such pre-stressed concrete structures. Okay, so the pre-stressing, I have told the steel in that's what the same story. The steel in RCC was playing a passive role. When the load is applied, well, then when there is a roll of steel comes, then if it is under reinforced, then the steel action will come. But here it is active roll, right? The steel is already under stress. Correct. So before even load applying, steel is already under stress. That is a big difference between RCC and PCC. Like sorry, not PCC, pre-stress concrete. What are the materials we are using? If we are pre-tensioning, I will tell you what is pre-tensioning, post-tensioning. It is M40, and we will use generally M30 and M40. You see the steel MPa, they are going up to 2300 MPa, mostly 1000 MPa, 1500 MPa. They will reach up to 2300 MPa. It's very high number, right? What used 250 MPa for mild steel, it is 110 times. Okay, so the understood the load, right? 2000 MPa means it's very big number. That much load it can take. And you see the steel wires diameter. So far we have discussed this 8 mm bar, 10 mm bar, 12 mm bar. Here the diameter of the steel wire will be 2 mm to 5 mm. Okay, then single wire, then it will be formed as a strand or tendon, combine everything that we will use. Okay, clear, right? Steel wire, we will not one wire can take this much load, obviously, right? It will cut. So you need 10, 100 wires bundled together to form a tendon strand. Please Google these words so that you will see what is pre-stressed cable. Okay, if you didn't understand. So I told you there are two ways of doing this. How to make a pre-stressed concrete is two way. One is pre-tensioning, another way is post-tensioning. What is pre-tensioning? We will tension the steel before, okay, before itself we will tension. Tension means same wire, same mild steel which is having 250 MPa, right? Obviously I will pull it up to a stress value of very high value. Like if I want 1000, I will stress up to 1000, 1200, so that with the loss at least I will get 1000. Okay, so pre-tensioning, you see the figure, I am pulling it, then I will cast the concrete, then I will leave it, then I will cut, so that the sudden release cut will make the concrete beam bend. This is a pre-tensioning method. Okay, then it is a pre-stressed beam, it is formed. Post-tensioning, everything is casted. You see everything is casted with the duct. Okay, there will be a duct and everything is casted. Duct is a pipe, small pipe, like a PVC pipe in your home. It will be a small duct. Then we will apply a steel inside. Then we will do the tension, post tensioning. After the concrete is casted, we will do the tensioning. Then you will have this one. Okay, so this is the two different procedure, pre-tensioning and post-tensioning. So pre-tensioning mostly we will use in sleepers. Okay, post-tensioning is exactly everywhere we are doing for other bridges, building roads, etc., wherever you are using. And pre-tensioning we will use M40. Okay, and for post tensioning we will use M30. This you should remember. And there are different methods based on number of cables you are using, and different, okay, which number of cables, 2 cable, 3 cables, etc. Those different way of post tensioning. Okay, and Lee Meccal system is very famous. They are using for 400 years old. That method they were using for wooden beams. Okay, so these are the two different methods. Okay, so I hope by this part you know what is pre-stressed concrete, right? What is pre-stressed concrete? We are going to stress the steel wires up to 1500 MPa, and then we will release sudden release, so the beam will bend in a upward deflection. When the load is applied, it will become straight. That's it. Okay, so I hope up to this you know. Give me a second. Up to this you know. Now we will move on to the next topic: how to analyze such beam. Okay, so you see a singly reinforced type of figure left side. Okay, but here we are having same location, some bars at a distance of eccentricity of E value. Okay, so when I am applying the load, after you you come to this figure, you see this figure on left side. I am applying the load, right? You see the third left side figure, third from the top. Okay, the last figure, cutting of tendon, that figure, you see there is a compression acting after cutting, right? After cutting, you understood the logic. I casted it, I cut the bar, so the bar will act as a compression. You can see that even in post tensioning, the behavior will be same. There will be a compression acting full time. Okay, so if there is a compression, okay, that is that P value, that the compressor pre-stressing force is acting over the steel wires. Okay, so that load divided by area will give you the total compression, right? That is P by A. That is the first figure. But this P into E, this eccentricity, this P will be acting as a moment over from the neutral axis, right? From the neutral axis, it will create a bending. Obviously, P into E will create a bending. It's like somebody, you are standing, somebody is putting high compressive force at your leg, at knee location. From the back side, obviously you will fall. Because why you are falling? You are rotating because there is a moment. Correct? P into E from your stability location. But somebody is pushing you with the same compressive force at your hip location, you just move 2 steps forward. So you are just sliding. But somebody is pushing you at your knee location, you will obviously fall down by rotating. So that is the moment it will generate. P into E is a moment divided by section modulus. I hope you know the formula. M by Z is nothing but a bending stress. Okay, so P into E is creating a tension at the bottom, compression at the top from the neutral axis. Okay, so the figure is little different. Remaining two figures are nothing but because of the obvious reason for the dead load. Dead load will create a dead load bending moment, right? If some dead load of structure weight, so that bending moment divided by the section modulus. Don't confuse with the T and B. T is at the top, B means bottom. Okay, T is at the top, B is at the bottom. So this is the overall stress which will act in the beam. One figure is first figure is because of the compressive force, total P by A. Second figure is because of the bending moment generated because of the pre-stressing. That will be acting little different. Positive at the bottom, negative at the top. Dead load bending stress M by Z, live load bending stress M by Z. Okay, so if you see, only if you consider only pre-stress, top or bottom, the formula will be P by A minus surplus PE by Z T by B. Give me a second. So actually it is not T by B, Z T by B, it is Z T comma B. Sorry for the formula. See, everywhere Z T comma B. The formula is wrong. It is not Z T by B, it's Z T comma B. Please listen. Sorry for this formula. When you are noting down, this is the first formula you are seeing in pre-test. Please note it down. It is not Z T by B, Z D comma B. When writing equation was horrible, I hope you know. So I did a mistake. It is like Z T by B. Okay. So when you are considering only pre-stress, so load because of compression, load bending stress developed because of that pre-stress. Only the two formula PE by Z. Okay, you can consider as a Z. There is no T comma B. Okay, so forget that if it is a rectangle, it is BD square by 6 anyhow. So if it is because of initial condition, okay, only due to pre-stress, okay, I hope you know that only they are considering first two figures. Only because they are giving transfer initial conditions, first three figure. Okay, M by Z. Okay, because of everything, then after servicing, consider like you made a pre-stressed beam, you want to know the capacity of the beam after 3 years. So you should include everything, right? Even live load, and then there will be a losses, right? So when you are pre-stressing, you are expecting 1000, you won't get 1000 because so many reasons, anchorage, shrinkage, so many reasons, you will lose the capacity. So I am putting some efficiency, eta P by A, eta. I am putting the two losses because of pre-stress, I am putting that formula md by z, ml by z. Okay, so these are the three cases. They may ask you in a question, only due to pre-stress, what are the stresses developed? During initial condition, before applying load, how many stress, what are the bending stress acting at the top and bottom? What are the during service, what are the stress acting at the top and bottom, using this formula. Again, I'm repeating, is it the formula is not z t by b, it is z t comma b, or forget t comma b, it is, you use it as z. Okay, so where p is the initial stress, as I told you, eta is the efficiency factor, eta p is the effective pre-stress. I told you there are so many reasons, for so many reasons this will have a loss. We cannot expect the same value, so we are having the theta value. Okay, so this is another condition, a transfer condition. Transfer means at initial conditions, top fiber will be under tension, because I told you, you can see the figure I showed you. Before applying load, that will be under tension. At service condition, obviously at service condition means it will behave like some normal RCC beam. RCC beam will have a tension at bottom, right? So that is the case. At transfer, at initial condition, top fiber will be under compression, tension. Okay, clear? If you understood this 2 point, you understood the total pre-stress concrete. Okay, so this is another story of we are still under pre-stress of concrete. How to calculate the moment of resistance for pre-stress concrete is nothing but C into L, force into distance only. Here in this case, we are, the distance is the distance because of two lines. There are two lines in pre-stress concrete, you should know. One is cable line, C line. Okay, center, you have to draw a line of the starting point and ending point. That C line is the cable line. P line is the pressure acting line. Compressive force will be very high at the center because of the load applied. So how the parabolic force, or it won't be parabolic, it can be linear also, the force line. Okay, the compressive force line is that P line, pressure line we can say, and C line is the cable line. Okay, the distance between them will be considered as a lever arm distance, because what is lever arm distance? It is the distance between where the C is acting to the where is T is acting. That is the lever arm distance, correct? So the L will be equal to, here in this case we are considering it as a M by P, because M equal to load into distance, P into L. From there they have taken L equal to, lever arm distance will be equal to M by P. Okay, so M is the bending moment acting. Okay, by P is the how much pre-stressing force we are applying. Okay, in this case you see the example here I have shown just simply for an example. It is a UDL load, so the bending moment will be WL square by 8. This is how the beam also will bend. So you have to apply a pressure to counteract the WL square by 8. Correct? How much? How will you know how much pre-stress to be applied? So you have a beam. They are asking you to apply pre-stress. How much you will apply? 1800 or something. What that number will be calculated based on the future. How you are considered as a UDL load, and the beam will bend with WL square by 8. Then you will apply that load. Then will you have a shape, right? Okay, I will show with an example. In this, from this slide, you should understand that it is, you should know lever arm distance is, they have calculating from force into distance. That concept, lever arm is nothing but M by P. Okay, so the P will be a constant. Remember that P is a pre-stressing force. That force you will apply will be a constant. Okay, so okay, so another one more thing I will, before that I will show an example how it is being done. So where you can keep your bar, you can keep your pre-stressing bars. That pre-stressing bar should be inside the kern area. Okay, kern or kernel area or core area. This core area you would know how to calculate for different sections. If it is a diamond shape, where it will be, for circular shape, where it will be. So for different shape cross sections, the kernel shape is given in strength of materials. I hope you should know that before. So if you know that maximum distance, beyond that if you keep the bar, it will develop a tension. Okay, so far I hope you know the story. When I am applying a pre-stressing, the total beam is under compression. When the load is applied, it will become a normal. Okay, so when you are keeping the kernel, this pre-stressing bar beyond the kernel point or beyond the eccentricity, eccentricity will be more, that will develop a tension. Okay, that, so there will be a limiting cable zone. If somebody is asking for rectangular beam, this is a formula, d by 6 to d by 6, below, inside that you should apply a bar, or else there will be a tension in the beam. There is no rule. Okay, you can apply and put reinforcement for the tension, no, not a problem. But this is the story. Limiting cable zone you should put within the core or kernel, so to have a throughout the beam compression. Okay, so I hope I will try to. So there are still some topics are there, but I will give you some examples so to understand what we spoke for last 5 minutes. A pre-stressed concrete girder, there are 10 meter span. Okay, they are asking for girder means beam, 10 meter it seems, 300 wide and 500 effective depth, has a straight cable. So the cable is straight, there is no different shape. Actually we can have different shapes of a cable inside the beam. It can be parabolic, it can be linear, it can be triangle. Okay, so they have given a straight cable with a pre-stressing force. They have given 800 kilonewton. 800 kilonewton is approximately 80 tons. Okay, it's very big number. At 50 from the soffit of the beam, 50 from the soffit of the beam is subject to a central point load of 500 kilonewton. They have given a point load. Locate the P line at the central span and also at the 1 by 4th of the span. They are asking you to locate the pressure line. That P line I showed you, like this P line. You can see this figure. They are asking for the P line and at center of the beam and also at the L by 4 distance of the beam. 1 by 4 of the span is length by 4. Okay, so this is your answer. So they have given load as a 500 kilonewton, length is a 10 meter, width 300 depth 500 pre-stressing force 800 kilonewton, and they told you like it is a simply supported beam with a point load. We know the bending moment formula, it is WL by 4, correct? So this will never change, right? Whether RCC, PCC or steel structures, any type of beam, whatever be the beam, this will be structural analysis, right? The simply supported beam point load at center will be WL by 4. So 500 into 10 by 4, which will give you the bending moment of 1250 kilonewton meter. You understood? The moment is very high, right? If you are smart, you know that in doubly reinforced section you would have studied to design a moment up to 200, 250, right? It will reach up to 270, 280 in flange beams. We never came across 1000 kilonewton meters. Very, very big number. Okay, so only we are going for pre-stressed. So bending moment is 1250. So at the center, okay, bending moment will be at the center is 1250. It is coming. We know the formula. We are going to shift. Lever arm distance is nothing but we are going to locate that M by P. We know M 1250, P is 800, divide, you will get 1.56 meter. So the P line will be at 1560 It is outside the beam. Okay, P line, the compressive force will be acting at very high, that much heavy force is acting, 1560 at 1 by 4 of the span. It is a, I hope if you remember the WL by 4, that bending moment diagram for simply supported, it's a triangle. So at 1 by 4 of the span, it will be M by 2, right? Bending moment, maximum at WL by 4. So WL by 4 divided by 2, WL by 8, that is a bending moment at that particular location, divided by that P value, it is not 2, yeah, it is 2, you are dividing by 2, it is 0.78, it is 780 This you can solve it by even similar triangle. When you know the central value, you can use similar triangle also to find that 780 Understood? By this problem, I hope you it is clear. I am able to make sure what is C line and what is P line, how to determine the P line for a beam. Okay, so if you didn't understand, go through this problem or solve yourself with UDL load or something, or with other cases, so that you know how to draw a P line and C line. Okay, so this one, and I will tell you one more problem. There is a pre-stressed concrete simply supported beam, again 6 meter span and rectangular cross section 300 to 600 and unit weight of 24 kilonewton meter cube, and the resulting pre-stressed tendon has a zero eccentricity at the ends and an eccentricity E at the midspan having linear profile. Very simple. Under initial condition, the allowable stresses are 20 MPa in compression and 2 MPa in tension. See, at initial condition, they have given these values. At initial condition means, I told you 3 cases, only pre-stress, then compression and bending because of pre-stress. At initial condition, you should consider compressive stress, bending because of pre-stress, and then you should consider the dead load. Okay, so that second case. So then they are asking how much pre-stressing force you should apply to tackle of this pre-stressing force and the eccentricity at the midspan they are asking. Okay, so you see the step 1, you should calculate the section modulus. So here it is a rectangle, so it is ZTRB, no issue, it is like a BD square by 6. I hope you know section modulus, it is I by Y, I is BD cube by 12 divided by Y is B by 2, D by 2, so it is BD square by 6, okay, 300 into 600 square by 6, and they have given, you should calculate the weight, they have given the density, you can see, you should calculate the dead load, right? I hope you know, you should calculate dead load, then only you will get the dead load bending moment, MD, to solve the problem. So dead load is density into area, multiply, you will get per meter, 4.32 kilonewton per meter, and the bending moment because of dead load is WL square by 8. They told it is a weight, right? Weight will be uniformly distributed. So WL square by 8, you will get a bending moment of 19 kilonewton meter. Remember, this is dead load. Dead load, so it is very less number, 20 only. Okay, if they are giving you live load, it will go up to 1000. So dead load they have given only 19. Okay, so stress at the top fiber will be, you know the formula, at the top P by A minus PE by Z plus md by z. Okay, this formula we have discussed earlier. P by A is because of compressive stress, Pe by z is because of bending stress because of pre-stressing, m by z is because of the dead load. So they have given at initial condition it was in tension, so minus 2 MPa. You can see they have given at initial condition 2 MPa is in tension, 20 MPa in compression. So minus 2 MPa for sigma t and 20 MPa for sigma b at bottom. So you just, if you see, it is algebra equation, right? You just cancel minus P by Z plus P by Z, cancelling each other, MT by Z minus MT by Z. You can cancel each other. So you will get 2P by A equal to 18. So you will get the P value, pre-stressing force. So you have to apply a pre-stressing force of 1000 to 1620 kilonewton. Okay. So 1620 kilonewton. Now you put this in the 20 formula. 20 equal to, because you know P, you know A, you know Z, you know MD, everything. Then you can calculate the where the eccentricity, where you should put the bars. Okay, solving this will give you the eccentricity of 135 mm. Okay, see, with this problem you can solve, you can pause and solve the problem. I hope after solving the problem it is clear how to calculate the pre-stressing force. If they have given live load, one more equation will come, that's it. Okay, so this is the same, they will give, change the numbers, change this one. This is how you should calculate the how much pre-stressing force to be applied and where you should keep your bars. Okay, eccentricity. So this is very important. Okay, please try to solve. And I expect the problems they can ask more problems only related to this stresses. Okay, P by A minus P by Z, only the same story. It will be very easy. You try to solve in textbooks if you have more and more problems, but they will only change the numbers here. The numbers, or they will give you live load also in this formula. Okay, so it's very simple. Okay, it's we'll move on. There is one more concept here, final concept before we are moving to losses, load balancing concept. So this will be very simple. Okay, so by using, we should put a suitable cable profile inside the beam. Okay, so that the external live load can be easily directly will be balanced. Okay, so if you put a bar so you see the first figure, left side top figure, I am putting a bar in a triangle way with some eccentricity at the center. If I put the bar like this, you resolve at the end, P will be resolved to P sin theta, P cos theta, P sin theta, P cos theta, right? So if you see, the W applied from the top will be taken care by 2P sin theta, correct? The shear forces whichever is coming will be taken care by P cos theta, correct? P cos theta is a horizontal force, so that will be taken care by P cos theta. Then if you equate also, you will get the same formula. That is the load balancing concept. The W live load coming from outside will be taken care by the P sin theta terms. Or one more way of explaining this is, if you see simply supported beam with a point load at the center, you draw the bending moment diagram. In the same bending moment diagram way, we will put the P line inside. Okay, this will be the cable profile, sorry, not P line, this will be the cable profile inside. If you put the cable figure inside, you will know how to calculate the P value. You see, bending moment will be calculated, you know, it is P into E. What is bending moment for this case? WL by 4, P into E. So if you know the eccentricity at the center, okay, so you put the P one side, bring everything this side, then you will know how much pre-stress to be applied. So if somebody tells you the W value and then they will tell you the support conditions, then you can tell this much pre-stress force to be applied, and this will be your cable profile. Okay, similarly, if somebody is giving you UDL load, so then what you should do, you should equate PE equal to WL square by 8. Then P will be equal to WL square by 80. Similarly, so the bending moment, if you know the strength of materials bending moment formula for different cases, you put on right side, bring the P this side. So how much pre-stress to be applied, you can use this load balancing concept to determine. Okay, so you can solve for different beam problems. Somebody asks you in 1 mark, you can use this concept to tell how much pre-stress to be applied also. Okay, so coming to the last topic in pre-stress concrete, there are two types of losses can happen. One is immediate loss. When immediate loss means after applying pre-stress, immediately what happens is there can be elastic deformation, right? What I am doing, I am pulling the bar, casting the concrete in pre-tensioning, and then I am suddenly releasing the bar. So the bar will come and hit at the concrete surface, so that there will be elastic shortening of elastic deformation. There will be shortening of the concrete. That is immediate loss. Friction, I am losing the friction inside, and there will be anchorage slip can also happen. I am expecting 1000, I may get to some 970, 980. Okay, so these three are immediate losses. Long term losses is like a shrinkage. Concrete will shrink in duration. And creep, we have discussed so much about creep in limit state of serviceability, and there will be a relaxation of the pre-steel. These are the losses you can expect. And anchorage and friction loss will not happen in pre-tensioning. If you are doing a pre-tensioning, there won't be any anchorage or friction losses. Okay, so what are the formulas if you are using elastic deformation? So how, what do you mean by losses? I should tell you, they will ask problem related to losses means I am expecting 1000 MPa. I got only 970 MPa. Understood? I asked for 1000 MPa, but I am getting only 970 MPa. After 1 year or after 6 months or after 2, immediately I got only 990 MPa, means immediate loss is 20 MPa. After 1 year I am getting only 960 MPa, means that now I lost 40 MPa from what I asked. This is losses. For how much MPa you are losing is the loss. Okay, the loss means it's not a single number, it is a stress. Okay, so the first formula to calculate due to elastic deformation is n into m into fc. Okay, n means number of wires, that leave that. M is a modular ratio, es by ec. If there are so many wires in the tendons, you should use this formula, but we will never use. If you are facing somewhere, you can use these formulas, but it is very simple. It is nothing but m into fc. Mostly they will give us a single wire. Okay, this means in problems they will give you as a single strand of wires, single strand. Okay, so m into fc is the formula to calculate how much loss due to elastic deformation. Okay, so m means modular ratio, steel Young's modulus divided by concrete Young's modulus. Concrete Young's modulus is 5000 root of fck. Fc is stress in concrete at the level of pre-stressing. At the level of pre-stressing, what will be the stresses? We have seen P by A plus or minus PE by Z. Same thing. Okay, same formula we will use, but at the level of pre-stressing, so the eccentricity will be 0. Most of the cases we will have P by A. Okay, so this will be the formula, n into m into fc. Most of the cases they are giving us a single wire. In the example problems, n will be 1. Okay, so loss due to shrinkage of concrete, I will show an example for elastic deformation, then we will come back. So you see elastic shortening, one problem. There is a rectangular pre-tensioned concrete beam has a give me a second. Okay, pre-stressed concrete beam has a straight concentric force with a pre-stressing force of 1000 kilonewton. Okay, so there is a 1000 kilonewton. The beam is 300 mm into 500 mm is cross section. M20 concrete they used. How much loss due to elastic shortening? It's very simple problem. They told you pre-stressing force 1000 kilonewton, beam cross section is given, FCK what they used is given. They are asking how much loss due to MPa. They have given an option. You can pass and solve. Anyhow, this will be your two-step answer. So this eccentricity M is modular ratio. Steel Young's modulus divided by concrete Young's modulus. Steel Young's modulus is 2 into 10 power 5. Concrete in 5000 root of FCK. So approximately 7.8. Stress in steel at the pre-stressing location, so that the eccentricity, the second term should be 0. The first term is P by A. P by A is 1000. They have given pre-stressing for 1000 10 power 3. Area 300 to 500. You solve, you will get the 6.67 MPa. So elastic shortening loss, I told you M into FC. So multiply both, you will lose 52 MPa. Okay, so you can calculate this before itself. You will lose up to 52 MPa because of elastic shortening. Okay, so I hope I made you clear. So we will go back to second loss. Second loss is shrinkage. Shrinkage is very simple. It is stress is nothing but Young's modulus into strain, right, by Hooke's law. So strain is epsilon SC, change in length by original length, Young's modulus of steel. Okay, they have given a constant value for estimating the strain because of shrinkage. For pre-tension case, it is a constant 0.0003, and for post-tension case, it is, they have given a formula 0.00t divided by log 10. It is log 10 actually, log 10 of t plus 2. T is the number of days. Okay, because shrinkage will happen, it's a permanent loss, right? It can happen after 90 days, it can happen 100 days, you can calculate even after 365 days, after 1 year also. So the T you should put in days. Okay, so it's very simple formula. This is like a strength of materials problem. Stress is equal to strain into Young's modulus. Okay, you know, right? Stress is directly proportional to strain, is equal to Young's modulus. You substitute the epsilon SC value from here, multiply by steel's Young's modulus. Most of the cases 2 into 10 power 5 MPa, you will get the answer. Okay, so I will have one more example for that. I will show that problem. So this a loss due to shrinkage of concrete at transfer of pre-stress in 3 months. 3 months is approximately 90 days. They are asking. So you know the formula for post tension, I think. Okay, they didn't mention, but this problem is for post tension. So 0.002 divided by log 10 of t plus 2, 90 plus 2. So you will get answer of epsilon SC, multiply it by 2 into 10 power ampere. They are losing 20 ampere. You see the answers approximately 20 ampere. You will not lose 200 and all. You will use 20 ampere because of shrinkage. Okay. So very simple. I hope I made you to clear how to solve shrinkage. Next thing is creep. Creep, I have mentioned so many cases before. What is creep, and I have explained clearly. So there are two things happen. One, because of creep of a concrete, means concrete will lose some stress, and steel also will lose some stress. Okay. So it is a direct formula, same m into fc, what we have seen initially for elastic shortening, but we will multiply with the creep coefficient. I hope you know what is creep coefficient for 7 days 2.2. I have given one table for 1 year 1.1. I have given one table in limit state of serviceability chapter. Same table, you take the creep coefficient for 5 value, multiply here, and do the same thing what you did for elastic shortening, m into fc. You will know how much loss of pre-stress happened because of creep in concrete. This formula. Okay. So in steel, it is called relaxation of pre-stress. We will say loss will be approximately 2% to 8%. Okay. So next, this is one of the loss which you will see only in post tension because of friction loss. Okay, you will not have any friction loss in pre-stress, pre-tension, because already it is tensioned. So your immediate loss it is also loss of pre-stress. Is formula is nothing but load into p naught into mu into alpha plus kx. Okay, mu is the coefficient of friction, alpha is the cumulative angle. Cumulative means you will sum the angle. If it is theta theta, it will be 2 theta, and you should put it as a radian. And k is the wobbling constant. Most of the case wobbling constant they will give in the question. Okay, x is at which location you want to find. You see, you can see the figure at which location. Okay, loss of pre-stress. And if it is a straight cable, if it is a straight cable, that alpha will be 0, right? There won't be any bending at all. It is a straight cable, so that term will go in only p naught into kx, wobbling coefficient, into the which location you are finding. Okay. So this will be I don't have an example now. You can find in your literature. This will be the extreme formula they can ask. You can shorten it for straight cables. Okay. So the final loss what I have now is loss due to anchorage slip. Anchorage slip is exactly the same formula, delta L by strain into Young's modulus. Okay. So delta that here the strain value is delta L by L. This delta L is because of anchorage slip. Okay, slipping of anchorage. And where delta is anchorage slip total. So overall, in overall I will come here. As overall what we have seen, what are the maximum you can expect is in pre-tensioning elastic shortening maximum 3% you can get loss. These are all in percentage. For creep 6%, shrinkage 7%, creep in steel I told you relaxation, so that will be 2%. In overall, in because if you do pre-tensioning you will lose 18% of your total stress. Means if you are expecting 1000 MPa, you will lose 180 MPa maximum because of all these losses. In post tensioning case, you will lose 15% only. Okay, 1% in elastic shortening, creep 5%. They are all match the followings they have asked in exams based on this table. Okay, you see, you should remember that very high loss is expected because of shrinkage, which is a permanent loss. Because of sudden loss, second highest is creep. Both are permanent losses. Okay. So elastic shortening, you see 3 or 1% is very minimum. I have one more problem. With that, we'll close the class. This a concrete beam. I have one more problem for understanding anchorage slip. There is a beam 300-meter span. Give me a second. Okay, it is 300-meter span. No, it's 30 meters. Sorry, it is 30-meter span. That's what 300 meter is very big. 30-meter span. You correct it. It is a 30-meter span. Is post tension by a cable carrying an initial stress. You see 1000 MPa, and they have given slip anchorage slip is 5 mm. They have given Young's modulus of steel 210 kilonewton is nothing but 2 into 10 power MPa. How much percentage loss they are asking? This is very simple, right? It is change in length by original length. Change in length is 5 mm divided by 30 meter, right? 30 into 30,000 into 2 into 10 power 5. They have multiplied this directly with that one. So you lose 35 MPa. But the question is percentage loss. So how much lost? 35 MPa is lost with respect to 1000 MPa. So 35 divided by 1000, you will get into 100, you will get 3.5% is the loss. You see the anchorage slip for this problem they have lost up to 3.5%. So if you see anchorage slip, I hope I made you clear. Okay. So with this we'll close the class. If you want more problems you can try in your textbooks. If you have any doubt please ask me. And This chapter try to concentrate for 1 marks losses topic. You try to solve 4 5 or 10 problems in losses, and you try to solve 1 or 2 problems in that how to calculate the p by s stress values, how much stress is acting bottom and top, and load balancing concept you will study clearly in your structural analysis classes also. Okay, based on equilibrium conditions you will see in that structural analysis classes also. Okay, so you try to concentrate on losses for 1 marks, more and more problems. It will be direct formula substitution. You have only 5 6 formulas, substitute direct, you will get an answer. And you try to concentrate on stress values. Okay, so if you want any problems or any topic, if you want more problems, please let me know. I will solve that 5 6 problems in that topic, and I can upload another video for you. So with that, we are closing the reinforced concrete course, and I am available all time. Please ask me if you have need any doubts or this one. Okay, all the best. Thank you.